everybody once more. I would like to warmly welcome you on the webinar, which is organized by our company, Nanovision. Today, we will talk about the batteries, battery materials, components, and analysis. My name is Jan Neumann. I'm CEO and co-founder of the company Nanovision, and I will be the guide and speaker today. The webinar we titled with, I would say, nice name, Unlocking the Secrets of Battery Materials. And we will dive into the AFM and SEM characterization, because AFM in SEM, this is what Nanovision is doing. I would like to warmly welcome also on the stage Tomáš Gazda, who is the expert in the battery field from the Brno University of Technology.
So thank you for invitation. My name is Tomáš Gazda. I work as associate professor at Brno University of Technology. I'm leader of Advanced Battery Technology Research Lab. We are focused on the research of lithium-ion and post-lithium-ion batteries. And our battery research lab have almost 50 years tradition in battery research field. And I'm happy to be part of this today presentation about AFM, because I think that AFM, it's quite new and advanced tool for deeper understanding of basics of the mainly anodes and cathode materials for lithium and post-lithium-ion batteries.
Thank you very much, Tomáš. We are shortly to start, but I would just like to ask you to do not hesitate to ask and raise your questions directly in the Q&A section. There is a team of my colleagues who will be very happy to answer your questions already during the webinar. So just ask whatever you have in your mind. So I think we are ready to start now with the presentation. Thank you very much. So brief, one more click, brief introduction about and the outline of today's webinar. So first I will make a short introduction about the benefits of AFM in SEM and why it makes sense to combine it together. Then I will ask Tomáš Gazda to introduce the current state of the battery research, also in industry, and challenging and possible solutions. So this is then I will follow with the solutions concerning in situ battery analysis, also including AFM-in-SEM. We'll also demonstrate the workflow of the sample preparation without any air exposure of the samples. And in the last session, last part, we'll also present several application examples, and actually we will demonstrate how powerful technique AFM inside SEM is for the battery analysis. By the end, there will be a short summary, of course, but we will have also the session Q&A, where my colleagues will pick the, I would say, most interesting questions. And together with Tomáš Gazda, we will answer them loudly to everybody. I will, since we have quite a lot of content, so I will directly jump into the most important part, which is AFM in SEM for us. So I would like to introduce the light scope. This is the instrument which you see on the picture. It's a small, compact, high-performance AFM system which you mount on the stage of the electron microscope. And with that, we say we merge the forces of AFM and SEM analysis. Just to give you the idea how the whole concept is, how the setup is concept. So you have the measuring head inside your SEM, and then you have just a simple feed throughs and the port where we take the electrical connection to our control unit, and then you have our NanoView software. So it's a very straightforward for the installation. It takes like 5-7 minutes. If you finish your job, you just take it out, and SEM can be used without any limitation. The question is why? Why to combine AFM and SEM, and why we focus on that in Nanovision? The point is that we have a AFM and SEM, well-known microscopy techniques, and each of them has a benefit. So AFM is super strong in the precise 3D topography with extremely high resolution imaging, but you can also measure the mechanical, electrical, or magnetic properties. The point is that with the AFM, you are touching the same surface with a very sharp tip. So the touch and feel of the sample, that's the benefit of the AFM. On the other hand, you have an electron microscope, which is ultra fast and extremely useful for the broader 2D imaging. You can also do the surface modification using a focus ion beam, which you will see today also. You can do you can analyze the composition of the materials using EDX, etc., etc. So the idea is to bring and take the best from the both worlds and bring it together. And this is what we offer with the Lightscope. So should I sum it up, what we see as a key benefits, the first of all, it's an in situ sample characterization. In the terms of the battery research, what we see is the most important is the vacuum. So there is no air exposure of the sample, and you analyze the same sample under exactly the conditions by the AFM, EDX, or electron microscope. The second part is a correlative multimodal sample analysis, because you can utilize different modalities of AFM or the SEM and correlate them together. Here I would mention the SEM visualization, topography, conductivity, or chemical composition. All of that can be directly correlated together because it's analyzed exactly on the same place. And the third part, third benefit is a precise localization of the region of interest. And thanks to that, you can select specific particles or region of interest where you would like to measure and perform the AFM analysis. So with all of that, we focus on the areas which are almost impossible to analyze without this combination, or it's extremely complicated and time consuming. I hope that we will prove it also today. I would like to also mention that we bring with our AFM tool into the electron microscopic community quite comprehensive modalities which we can measure. So it's you can analyze mechanical properties like subnanometer topography, surface roughness, local elasticity or hardness. You can analyze the different electrical properties like a conductive mapping, which you will mainly see today. But we can also measure surface potential using KPFM technique. You can measure different local electrical properties. You can analyze magnetic properties, or in this case, sorry, piezoelectric domains. You can analyze magnetic properties. You can perform different spectroscopy, IV curves of or FZ curves. And you can also perform correlative microscopy, with the technique which we call correlative probe and electron microscopy. All of that can be used in the broad areas. Core, I would say, is a material science, fantastic tool for analysis of 2D materials or metals or batteries. This is why we are here today. Or you can analyze different nanostructures prepared by the focus ion beam or gas injection system or any others. You can use it for analysis of semiconductors, especially failure analysis or dopant concentration analysis, or in the life sciences field. So it was a very short intro about why AFM in SEM is so powerful. And with that, I would like to invite to the stage Tomáš Kazda to give you the introduction to generally the battery field, the research and trends. So Tomáš, floor is yours.
Thank you, Jan. So I will tell you something in the short time about the batteries. So mainly lithium-ion batteries. Currently, the lithium-ion batteries are on the market almost 35 years. During the time, they give us possibility to set up several new applications like EVs, electric motorcycles. Currently, they are used in many applications like smartphones, notebooks, electric tools, And the biggest applications are energy storage systems with the capacity currently even more than 1,000 megawatt hours. Worldwide, production of the lithium-ion batteries, which are the main type of batteries on the market. Second one are lead-acid batteries. It was in 2022 around 720 gigawatt hour. And the main applications was electromobility, mainly in China, then in west part of the world. Electronic devices, other applications like, for example, some smart like tools and energy storage systems. We predict, or generally the prediction to 2030 is that worldwide capacity of production of lithium-ion batteries will be 3,300 gigawatt hours, and the main application will be still electromobility. And from my point of view, the second most interesting application for the future will be energy storage systems. To be like more in touch with the numbers, because these numbers are quite huge, and I think that just few people are able to understand these numbers correctly. I mentioned like few numbers about the electricity demand globally. Per 1 minute in 2022 was electricity demand 46.4 gigawatt hours. And in Germany, for example, 1,500 gigawatt hours, and for example, in Czech Republic, almost 200 gigawatt hours. So if we, for example, take all batteries which was produced in 2022, and if we put them in, for example, Czech Republic, and make from, if we set up like these big energy storage systems with 720 gigawatt hours capacity, we will be able to store energy which cover daily consumption of Czech Republic for a few days. As I mentioned, the batteries, lithium-ion batteries, are on the market quite long time. It was introduced in 1991 by Sony, and energy density of these batteries was 80 watt-hour per kilogram, and the price $3,200 per kilowatt-hour. And thanks to the optimization of the production process and upscaling of production process, the energy density and development of the batteries as well, the energy density increase close to 300 watt-hour per kilogram, and price decrease close to $1,000 per kilowatt-hour. And in the next few years, the price will be even lower than $100 per kilowatt-hour. So lithium-ion batteries are like most currently important type of the batteries on the market from the point of view of the final application. And in the future, the price will be probably lower and energy density even higher. The same like any other kind of the batteries, the batteries is based on several parts. The main part are anode and cathode, separator, electrolyte, and case. We have the main three type of the design of the cells: cylindrical, prismatic, and pouch. All of them are used in electromobility, for example. Each type of cell have some advantage and disadvantages from point of view of, for example, safety, stability from the case stability and thermal behavior and C-rate behavior. But that's for other presentation. The basic principle of function of lithium-ion batteries are the intercalation of lithium ions from anode or from cathode to anode and back. The lithium is mainly in cathode, which is based on lithium metal oxide, usually metals like manganese, cobalt, nickel. And the anode is based usually on graphite. And the electrolyte is mixed of solvent like dimethyl carbonate, ethylene carbonate, and lithium, different kinds of lithium salts. In the case of the cathodes and anodes, there are several types of cathode materials. Like the most important type are lithium iron phosphate and currently lithium nickel manganese cobalt oxide. But generally, we have like 5 families of cathode materials, 3 families of anodes. The main of anode material is graphite, then LTO and silicon, but silicon is used mainly like additive. That's big advantage of lithium-ion batteries is that we have quite a lot of materials which can be used on the anode and cathode side. That each of them have different properties, like electrochemical properties, electrochemical behavior, and for example, the thermal stability, structural stability. So we can set up the batteries, the properties of the battery based on the materials which we use on the electrodes. In the figure 6, you can see the different discharge curves of cathode materials. As you can see, the working potential, it's different if we have a lithium iron phosphate or if we have lithium nickel mangan cobalt oxide. So we have to understand the behavior of each materials to be sure that we work with the battery with proper way, and we cycle them, for example, in right potential windows. In the case of anodes, the situation is the same. Currently, the most common material is graphite. The graphite have quite low discharge and charge voltage against the lithium. LTO with like material for applications which needs high cycle life, for example, and high stability. And the silicon have quite big capacity, but this material is unstable, so it's used mainly like additive together with graphite. And again, each material have different working potential windows and different capacity. So we have to understand quite properly to behavior each of these material. The battery are usually tested by long-term cycling. We can cycle them in different C rates. So it means like the current which we apply for the charging and discharging and batteries, it can be set up like to different rate, so the battery can be charged and discharged like faster and slower. So if we discharge the battery faster, like this red curve in picture A, you can see that if the rate is higher, the degradation is also higher, the capacity decreases faster. Then the other thing which have influence to the degradation of the batteries, and it's test its working window. So if we test the cycle of the battery in the full range from 0 to 100%, the degradation will be much faster compared to the cycling in the not that deep range, for example, like 75%, from 65 to 75%, as you can see on the yellow curve. And the other thing which have influence to the properties of the battery is temperature. As you can see on the picture C, if we change the temperature, if we increase the temperature, usually capacity is higher. If we decrease the temperature, we increase internal resistance and the capacity go down. And also from the point of view of a cycle life, if we increase the temperature, we usually quite decrease the cycle life of the batteries, and the same if we decrease the temperature. But in the case of the low temperature battery, is not that sensitive compared to the higher temperatures. Degradation processes can occur in different part of the battery production and use. Some of them are connected with the design of the batteries, so with the design of battery modules and cells. Some of them are connected with the production, like cell structure and electrode structure. And some of them are connected with the application. So if we cycle the cell, we usually, for example, make some volumetric changes of active materials. So we can see the changes of the active layers or changes of the particles itself. In this case, we can see the particles with some core shell structure. So there are different ratio of the nickel inside particles and outside. So during the cycling, then can be also some diffusion of the nickel ions or manganese dissolution also. Then we are focused on also to studies of interfaces like solid electrolyte interface on the anodes, or in the high and really deep research on the studies of the atomic layers, for example, lithium hydroxide on the surface of high nickel content NMC. There are several possible ways how batteries can degrade, and the particle point from the particle point of view, like particle cracking, safe formation, some dendrites formation, and loss of connection between the binders. And all of them we can see by, for example, by SEM or by AFM. So that's all from my side, and I will give you the floor to Hansa.
Thank you very much, Tomáš, for the introduction into the field. And I think it's quite clear that the demand to improve the battery storage and energy storage capacities is significant. And I think it's also our duties as a company to bring the solutions which can resolve the problem. So right now, I would like to offer one of these solutions concerning AFM inside the SEM. I know I will come back, but if I just would like to summarize what we will talk about and what Tomáš just said. So basically, batteries charging and discharging is about the process when the lithium ions are moving from cathodes to electrodes. So it's ionic conductivity. It's a movement of ions, not the electrons. So this is one part, and this is what we will study and try to describe also. And the battery research, we see that we can offer the solution for analysis of the individual components, like the cathode active materials, solid or liquid electrolyte, solid electrolyte interfaces or anodes, where, as you could see, there are different materials are used and needs to be studied. But also we can study the processes, how actually the fundamental battery processes, how it works in the different materials, was the energy density, how charging and discharging affects different materials, and of course was the lifetime and battery safety. And on the last part, we just need to look at the performance itself and the lifetime, because each degradation process or each component influence and affect the performance of battery itself. So if we go for the macro analysis, now we dive into the micro analysis. So I just would like to announce that battery materials are not the easiest way to measure. Many of you are, I believe you are very experienced. Why? One of the point is they are very air sensitive because of the lithium. So any air exposure may affect and complicate the further analysis. We talk about the complex system, about the anode, cathode, electrodes, degrading and changing during the cycling, and also new materials and new components, new structures are coming in and are studied. So here we believe that in situ correlative analysis approach is simply needed to be able to understand what is going on and what are the properties of our materials. So here I would like to show you, demonstrate you the workflow for sample analysis. And I would like to announce and thanks a lot to Thermo Fisher Company, because for more than a year we are working together to provide such a solution. So basically, I would like to introduce two ways how to prepare samples in proper way. One of them, first of them, which we call ex situ sample preparation, is using broad ion beam milling to making the cross section and polishing the surface. Another approach is which we call in situ sample preparation, is using focused ion beam directly installed inside the SEM. I will briefly describe both of them. So for the ex situ sample preparation, we of course start in the glove box to protect any air exposure. And then, or where in the glove box you can do the cycling experiment, etc., etc. Then you can use a so-called clean connect transfer, where you can, without any air exposure, transfer the sample into the clean mill. It's a product from the Thermo Fisher doing the broad ion beam milling to make a cross section and prepare the sample. Again, use a clean connect transfer and directly move the sample into the electron microscope, which is already equipped with the AFM. So this workflow we can also show you on the video. So you have a glove box. On the side, you can open the port. You put there, mount there the clean connect transfer chamber, which enables you to transfer the sample without any air exposure. It's quite straightforward. You just move in the sample holder. You mount the sample holder to the rod. You put it into the transfer chamber in the clean connect. You close it. You can evacuate the transfer chamber. And now we are ready to take this part into the broad ion beam milling, in this case, clean connect, where again the process is optimized, that no exposure is evident. In the broad ion milling, we take the sample, we polish it with the broad ion beam, and after that, again, you can use a clean connect and bring the sample after the cross-section preparation into the electron microscope. You can evacuate the transfer chamber, and now you will see what you see on the video is that how the sample is going inside the SEM already equipped with the light scope. This is our AFM. So then when you continue, it's just the work with the SEM. So you can navigate your AFM tip to the region of interest and start to perform your analysis. So this is workflow which we have developed. The advantage of using broad ion beam is that you can prepare relatively large areas and large cross sections where you have many active materials, in this case cathodes, and then you can choose which one you would like to analyze further. Another approach is in situ sample preparation, which means, excuse me, we are using the focus ion beam directly inside the SEM to prepare the cross-section and the sample. Then the workflow is a bit of different because we directly take the sample from the glove box and we put it directly into the SEM, equipped, of course, with the focus ion beam and gas injection system and the AFM. If we want to prepare the cross-sectioning, so we have developed the workflow as follow. The first, you can tilt whole AFM with the sample towards the focus ion beam, and using the gas injection system, you can build so-called protective layer. Then, under the angle of 15 degrees, you can use a focus ion beam to prepare the cross-section on the sample. And then in the last step, you can approach with the AFM tip and directly analyze the area of interest. So all of that is done inside the SEM. So we have a visualization of that. So you see now how the protective layer is growing. Then the next step is a rough fit milling. So we are preparing the cross section, which we follow with the focus ion beam polishing to prepare the better surface. In this case, it's not the optimal, it's just the visualization. And then, of course, you can use a SEM to exactly pick which cathodes you would like to analyze. Then you can come with the AFM and start the measurements. There is a different approach if you would like to analyze and make a cross-section of specific particle. So in that case, it's also quite good to cover everything by the conductive platinum. Then use a focus ion beam to make a cross-section, and which results in the cathode, exactly the specific cathode or particle, which is completely covered by the conductive platinum, and then it's a fantastic for all the different analyses. With that, I would like to just show which instrumentation was used for the applications examples, which I will show you later on, and which is optimized for such a work. Maybe also another point is what you have just seen, this workflow, it's absolutely unique. So we are unique and only one who is able to transfer the sample directly from the glove box via the broad ion beam to the SEM equipped with the AFM. So what instrumentation we use? It's a glove box protecting box with argon or nitrogen atmosphere. Then we use a clean connect for the broad ion milling, which provides a different benefits like ultra high energy, rapid surface cross-sectioning or the polishing. And the second part, on the SEM part, we use Aprio2 from the Thermo Fisher Scientific, equipped with the EDS, with the AFM-in-SEM technology, enabling the fantastic analysis of the surface composition. We use the clean connect, as was mentioned, where the key benefits is straightforward, that you can use it for transfer to samples from the glove box to broad ion mill to your SEM or dual beams without any air exposure. It can be also used as a cryo stage, and actually it's also compatible with Thermo Fisher TEMs. And the last part is our light scope, AFM inside the SEM, specifically developed for in situ multimodal correlative analysis, which enables you to really make ultimate performance measurements inside the SEM. Here I would like to highlight some specifications. So the area which we are able to measure is 100 by 100 microns, roughly, with the 40 picometer noise floor in the Z range. we offer, as I mentioned, different modalities which you can use for the analysis, and it's also compatible with most of the accessories: the focus ion beam, gas injection system, EDS, EBSD, cathodoluminescence, and others, and also with the different transfer system like clean connect or normal load lock, or the quick lock. We have a quick lock system which we are also compatible, which is from the Quorum company. With that, I would like to dive into the showcases, examples, how we use in situ analysis on the real samples. I would like to say something about the samples which we used and give you a bit of intro. So we were working with the lithium-ion batteries, in this case with the solid-state electrolyte. The architecture you can see here on the picture, where there is a current collector, conductive one. Then there is a cathode tape. Actually, it's a mixture with a solid electrolyte, and there is a solid electrolyte itself. So then for the preparation, we just prepare the polishing surface, as you see over here. So this is the area, basically, which you will see later on, which we will analyze. Some of the examples we will show also the lithium-ion batteries with the liquid electrolyte. The structure is a bit of different. You have a cathode tape, where is a collector and where is a cathode materials. Then there is a separator and the liquid electrolyte in between. Of course, for SEM analysis, we cannot use a liquid, so you will just mainly see the cathode tape, and there is an anode. Again, for the sample, what you will see is mostly the cathode tapes, where we made the cross section in this way. So you can see the cathode particles, and also quite often the aluminum collector, current collector. I would like to highlight also one, or describe one more feature, which is actually the cathode particle itself. So what you see here, it's a cathode tape prepared by the broad ion beam polishing, and I want to focus on the cathode particle. Cathode particle itself, which is called secondary particle, is composed by different primary particles, which are composed by cathode active materials. So these are the different things, because during the charging and discharging, there is a plenty of effects which are going on within one particle. So I just would like to describe a bit how the cathode are structured. We will also do quite a lot of analysis of conductivity. For that, we will use a conductive AFM, which works in a pretty simple way. So we use a conductive AFM probe. We bias the tip or the sample, and then we measure the current. And because we are scanning during the measurements, we are collecting the conductivity maps. And this is what you will basically see this setup on the real samples. So we have an AFM tip, which is touching the surface, and then we connected the collector, and we are measuring the current flowing in this circuit. First application example is kind of the bit of basic. So it's just analysis of cathode tape. We call it inspection. What's the interest here? So on the picture, you see cathode tape, and we are interested to be able to localize different components in the cathode tape, set their or determine their composition, but also check and validate the functionality, mainly from the electric properties. For this sample, we will use NCM particles, solid state electrolyte, after 200 cycles. So always I will just notice which kind of the sample you will look at, so then you can understand what you see. When we talk about the inspection, so basically this is what you see using the SEM, where already in the contrast it indicates some components. Using the EDS, the chemical composition, you can directly analyze the localize and identify different components. So we see solid electrolyte, which has the sulfur. We see cathode active materials with oxygen, and you see carbon here. And you can see how it's correlated with the contrast. Adding the measurements of the conductivity and conductivity mapping, we actually directly confirm the proper function of each component, because the solid electrolyte supposed to be very conductive for ions, lithium ions, but should not be conductive for the electrons. And we measure electric conductivity, and this is exactly what you see here. So it's dark. We see on the carbon, which is additive, is highly conductive as it's supposed to be. And also you can see the different contrast of cathode active materials. So you can validate that each component play the role as it's supposed to be. Now we will have a look into the cathode materials or tapes with the mixture of the materials, and we see how we can analyze it with in situ. So what we will focus of identification of different active materials. We are focused on the conductivity and the differentiation between different materials. Also, we'll highlight some failure analysis and correlative analysis. So this is how the sample looks like. Again, we talk about the sample which is composed from NCA and NCM particles. This is the liquid electrolyte battery. It's a pristine state. So this is what we have used for this experiment. So the components identification again. This is a picture which you see in the SEM. We use EDS to analyze different elements. So with the aluminum, so immediately visualize the collector. And using the composition of the mangan in this case, we can distinguish nicely between the NCM and NCA grains and cathode materials. Taking that, we can directly say on such a picture, then this is a collector, this is NCM particle, NCA particle, this is NCM particle, and we can continue with the conductive mapping. This is exactly performed on this area. So straightforwardly, you see big difference in the conductivity of the particles, or both particles, actually much more than expected. So what we see is on the NCA is about 3 nanoamps. On NCM, it's 0.05 nanoamps, so 3 order to magnitudes difference, which is more than expected. So once we talk and present this result to the expert, they immediately realized that probably something else is also playing a role to enable to explain such a difference, which is a delamination and evident crack in this area, which is actually another important topic. The problem is the delamination of the cathode materials for the collector, which means the conductivity is falling, which means the performance of the battery is going down. So these kind of the measurements can be directly used for the study of delamination processes also. And by the end, on the third part is we can have a look and analyze the conductivity of the cross particles on the cross section. In this case, it's a carbon, so we see it's a heavily conductive. So from this one analysis, it can be used for 3 different studies. And now you can imagine that you have a different materials, different compositions after the different stages of cycling, etc., etc. All of that you can reveal using AFM, SEM, and EADS together. We talk about the correlative microscopy, so we want to just show you how nicely you can correlate all informations which you have together from topography, conductive AFM, SEM, and EDX, taking from exactly the same spot under the same condition. You can put them together, you can correlate them, and then you can again start to understand what is going on, what's the correlation between the chemical composition, conductivity, surface roughness, etc., etc., which really gives you deep understanding of the processes and composition and properties of your batteries. So now I would like to have a look how we can analyze the impact of cycling, actually degradation of cathode active materials. I would like to come back or remind briefly how the cathode active materials is behaving during the cycling. So basically the lithium ions are going in and out. It's a charging and discharging process where the lithium is going inside the cathode materials. And actually the whole particle is kind of the breathing because it's changing the volume, which cause a problem, which because induce the cracks, internal cracks, which again affect the conductivity and affect the performance of overall battery. So what we can do about it? So we can raise the question how cycling affect the conductivity itself of the cathode active materials. So this example, which we will show you, is on NCM particles with a solid electrolyte, and we will compare the pristine state with the sample which was cycled by 200 times. Before that, I will try to jump out for the macro approach and point of view. It's known in the literature that if you are charging the batteries as a whole, and you analyze charging and discharging and cycle the batteries, and you analyze the resistivity of the battery. So after certain numbers after initiation phase, the resistivity drop. So we see that there is about 50% drop after 150 cycles. What can be done in the studied and how it can be explained in the micro scale. So what you see here, it's SEM images of the NCM cathode tape on the pristine stage and after the cycling. So there is not that big difference. Maybe you can start to see the crack, etc., etc. But then we can start to think about the conductive measurements and conductive changes. So this is how the conductivity looks like after the 200 cycles. And then if we dig into the details, we can select the area of interest in the reasonable areas where we have some cathode materials and the areas which we can compare. So we can zoom in and make SEM images. And then on both areas, we can measure the conductivity using the conductive AFM. It's a conductivity on the pristine NCM cathode, and this is the conductivity after the cycling. I will no doubt that the quality of the images is not the best one, is not for the nature for sure, but it serves for the value because it tells us exactly what we are interested about, which I will just show you. So directly, what you can see that we can see the very bright spot, which is increase of the conductivity. In the first stage, I will not focus on that. We'll focus to analyze on the changes of the average conductivity on the cathode materials, which you can see here. We average it, so we are finding that the quality of the image is not the best one. And what we can clearly state is that the resistivity drops significantly from 130 gigaohms in the pristine stage to about 21 gigaohms in the after 200 cycles. So we see 85% resistant drop after 200 cycles. So you see as this corresponds to the behavior which we observe in the macro scale. And then we can follow up a bit and we can think about how actually cycling affect the conductivity on the grain boundaries of the cathodes. This is what you see also before. We'll use the same samples, NCM particles, solid state electrolyte after 200 cycles. And this is what you see. You can see the conductivity, different areas, but on the cathode materials, you see areas which have a significantly higher conductivity. It seems to be as on the grain boundaries. One might say it's an influence and it's an AFM artifact because of the tip interaction on the topography level. For that, we utilize the benefits of correlative microscopy. So we try to dig directly inside and find the area. We have a topography changes, and we also can see the different conductivity. And so we can confirm that we do not talk about the AFM artifact. This is our real changes of the conductivity. Then we can make a plot within this area, and we see directly three different levels on of conductivity, actually, and the conductivity change in more than 3 orders of magnitude. I'm sorry. So with that, we can come back and we can ensure that the conductivity is rising on the grain boundaries. So this is what we see is not a fake. And we in level of 3 orders of magnitudes, and again, after the discussion with the expert, it's suspected that there is a diffusion on conductive materials from the cathode to the grain boundaries. So this tool is fantastic for studying these processes, which again influence the performance and lifetime of the battery. Another point of view, which I would like to highlight, is interparticle connectivity. As we were discussing, the particle is breathing during the cycling and the cracks are appearing. So the question is, how cracks affect the conductivity inside the cathode itself? For that experiment, we use NCM particles, liquid electrolyte after 200 cycles, which means the cracks are already there. This is how it looks like. So again, you can see the collector, you can see nicely the particle which we have selected for the analysis. On this SEM image, you can already see the cracks, which are visible, and also the areas which shows a different contrast in electron microscope. And I'm coming back. The question is how much these cracks affect the interparticle connectivity. What we can do for that, we can again use a conductive AFM, measure the conductivity, and clearly see the difference in the conductivity in the region in this region. If we plot and make a profile of the conductivity, we nicely see the regions with again 3 orders of magnitudes difference in the resistivity. So we talk about 300 gigaohms compared to 0.3 gigaohms. So this is not a negligible and it's not an error. This is the fact. And actually, this technique reveal, identify, and localize the particles which are disconnected from other areas. So failure analysis. The last topic, the last example which I would like to show is a intra-particle conductivity mapping. So as I explained, we have a primary or secondary particle, which is composed from the small particles, primary one. And the question is, how is the conductivity the same for all of them or it differs? So for them, we use the NCM particles again, so with the solid electrolyte in the pristine stage. But in this case, I will show it on in situ sample preparation. Just to remind you, we use a focus ion beam to prepare the cross-section directly inside the SEM, and after that we directly measure. So this is the schematics, how you can see it. So these are the particles or cathodes which we can select for the analysis. This is the AFM tip. This is the area which we have selected for the for the analysis, and then again we can correlate it with the conductivity map, and directly we can see how different grains reveals different conductivity. So again, this is very important how the materials is behaving before the cycling, after the cycling, etc., etc. You can correlate it with the SEM again, and even more, you can highlight another interesting feature. For example, the conductivity on the areas which should not be conductive, we do not see in the SEM, etc., etc. So, very powerful technique. So with that conductivity mapping, can help you to reveal the differences in individual primary particles. With that, I would like to conclude, I would say quite condense webinar and summarize it. So what we were trying to show and demonstrate is that AFM-in-SEM is a very powerful tool for battery research and development. Tomáš Kazda tried to explain and show you some challenges and trends in the battery research in general. You saw some battery components, materials, performance, price, and so on. We have demonstrated the solution for in situ battery analysis. We demonstrate you in situ correlative analysis on specific place with the optimized instrumentation. We try to demonstrate a unique workflow with the sample transfer at no air exposure. And then some application examples. We are mainly focusing on the cathode active materials, trying to show you different conductivity, chemical composition, etc. We showed you how to analyze the mixed materials with mixed cathode, impact of cycling to the cathode conductivity on the bulk, on grain boundaries, and inter and intra-particle conductivity. I believe that today we were able to fulfill what we have promised. So we demonstrate to you the solution enabling to unlock the secret of battery materials, and we dove into the AFM-in-SEM characterization. I would like to once more thanks to Thermo Fisher Company to doing with us together the project and be able to offer this solution to you. Please stay in touch. There is plenty of opportunities where to meet Nanovision. Go to the webinar, go to the web page. You can meet us on the social media. You can see a lot of materials on the YouTube. You can meet us in conferences, or please just write us directly, raise the question. With that, I would like to move into the part for the questions and answers. So thank you very much to all of you who were raising the questions. I guess you have got a lot of feedbacks already, but again, together with Tomáš, we will stand up and try to answer some of your questions loudly. So if we are on the stage again, right now it should be. So I see here one question, so I will just read it and then answer. How accurate to probing and quantify size, location, surface, inner surface, catalyst, nanoparticles on porous carbon black? The NNP is about 2.5 nanometers, located either on the surface or inner surface of the carbon pipe. So it's a bit of tougher question, I would say. Precision of the navigation and probing, this is quite precise because you can use a electron microscope. About the ability to measure such a 2.5 nanometers particles, for that case, I would be much safer to test it and try it. So feel free to send us the sample. I believe that we can do it, but I don't want to promise anything from the spot. So get in touch. We will be happy to measure it. Maybe I can ask Tomáš to.
Yeah, if you want. Yeah. There was two questions connected with the batteries. First one was why NMC and ACA cathode material is not used in prismatic or larger cylindrical batteries. Only LFP is used. I think that NMC and NCA cathodes are used also in the large prismatic and cylindrical cells. So in the case of the prismatic cells, the capacity is like even higher than 100 amp hours. In the case of the cylindrical cells, for example, Tesla have its own format, 4680 cylindrical cells. These cells will be based probably on NCA because it's main cathode material in the case of this Tesla. But BMW, for example, in generation 6, it's like new generation 6 cars will use also the cylindrical cells with its own design, 4695 and 46120, and the capacity of the cells will be also quite high, and these cells will be based probably on high nickel content and MC. It was first question. The second one, it's connected with batteries, but it can be also connected with AFM and analysis of the samples. Nitrogen in Glaubergs will be counterproductive or not. It depends on the type of the samples. In the case of cathode materials itself, nitrogen is not problem, but in the case if you want to study the pure metal lithium, nitrogen will affect the sample, the surface of the lithium. So it highly depends on the type of your work and of your focus. But in the case of the pure metal lithium, or in the case of the pure metal sodium, I recommend to use argon instead of nitrogen.
Thank you very much, Tomasz. Maybe I would like to conclude that today our aim was not to do the scientific job. Our aim was to inspire you and show you what could be possible. We understand there is a plenty, thousands of different experiment materials, etc., and we should need to look at each of them specifically. So I hope that we did our job and inspire you how to improve your experiments with the batteries using AFM inside the SEM. With that, I think it's time to thank you very much for your time, for your attention. I would like to once more thank you, Tomasz, to joining us and give us the feedback and support from the expert point of view. Get in touch. Let us know. Thank you very much for your attention. Have a nice day.
Have a nice day.